Okay, so for FRQ number 2, we have a block of mass m, and there is a force of magnitude F acting upon this mass horizontally, as shown in this figure. And the block is on an inclined plane that is making an angle of theta relative to the horizontal. We are also given that there is friction between the surface of the block and the surface of the incline, and the coefficient of friction is given to be just mu. Okay, so part A wants us to draw a free body diagram of the block and label all the forces that act on the block as it slides up the plane. Okay, so let's do this. So here's the incline. And here's the block. It has a mass of m. We have a force of F acting upon it right here, as given. For any object, there is gravity acting on it, so there is a force of Fg. Now, since this is on an incline, there's going to be components to my Fg and my F. So first of all, for my Fg, I have Fgy, which is perpendicular to the surface of the incline. Fgy. And I also have Fgx over here, which is parallel to the surface of the incline. For my F, the component that is parallel to the surface of the incline would be, let's call this Fx, and this is what it looks like right here. The component is perpendicular to the incline is this, Fy. And we also have friction, so there's Fk. So those are all my forces. I finished part A, but in addition to it, I'm going to the side define all my forces, so I can just plug them in later instead of having to worry what they're equal to later. So first of all, my Fg I know is equal to mass times gravity. Building onto that, Fgx is going to be equal to Fg sine of theta, as it is on an incline, which is mg sine of theta. Fgy is going to be equal to Fg cosine of theta, which is equal to mg cosine of theta. Now for my components of the forces that is applied on the object. So my Fx, basically this angle right here, this theta angle, is the same as this theta angle right here. So this is going to be equal to, Fx is equal to F cosine of theta, and that leaves Fy is going to be equal to F sine of theta. Oh wait, I forgot to draw my Fn's. Okay, my bad. So here's Fn right here, and Fn is equal to Fg right here, Fgy plus Fy, this force right here. And so that means that Fgy is mg cosine theta, and Fy is F sine of theta. So that is what Fn is. I also have an Fk. So Fk is equal to mu times Fn. And Fn I just defined up here, so it's equal to, so Fk is equal to mu times all of this. Mg cosine theta plus f sine of theta. Okay, so now I've defined all my forces. Now the following problem should be easy. So B tells me to develop an expression in terms of m, theta, f, and mu and g for the block's acceleration up the plane. Okay, so part B. So for this, I'm going to use Newton's second law. Total force is equal to mass times acceleration. And for this problem, it's this acceleration parallel to the incline. So this I'm calling this x. So total force in x direction and max. So since it's going up the incline, I know my f is going to be the biggest. So my fx minus fgx minus fk, those are the forces that are parallel to the surface of the incline, and fx is the biggest, so that's equal to max. These two are composing fx. Okay, so I define all of it up here, so I'm gonna plug it in. So fx is f cosine theta, fgx is mg sine theta, fk is all of this up here, yeah, minus mu times mg cosine theta plus f times sine of theta, and that's going to all equal to m times ax. Okay, so right now I'm going to distribute the mu to the terms in my parentheses. So all of this is the same right here. And I'm going to distribute the negative mu. So I'm also distributing the negative. So this is going to be equal to mu times mg cosine of theta. That's the first term. And this is going to be minus mu times f sine of theta. That's the second. And that's going to all go to max. Okay. So right now, I'm going to group certain terms together. And I'm going to group terms that have the same f. And I'm going to group terms that have mg together. Right here. Okay, so once I group these two together, I'm going to take out or factor out an f. So factoring out f, I have cosine of theta, and then minus mu sine of theta. So that's that's one part. For the next part, I'm going to factor out a negative mg because both of the terms with mg have a negative on top, in front of their terms. So I'm factoring out a negative mg, and so this term is sine of theta left. This is plus cosine. Wait, I forgot the mu. Plus mu cosine of theta. That's still gonna be max. So I was trying to solve for ax, so all I have to do is divide m over. So ax is gonna be equal to all of this and then divide by m. And that is it. This is my equation for acceleration. Okay. Part C wants me to develop an expression for the magnitude of the force F that will allow the block to slide up the plane with constant velocity. What relation must theta and mu satisfy in order for this solution to be physically meaningful? Okay, so first of all, once again, I'm going to use newtons. So delta total force in the x direction is equal to max. And I was told that I want my force to be at a certain point where the block will slide up at a constant velocity. So that means ax will be equal to 0 meters per second in this case. So that means once I plug in my my forces, I have fx, basically the same as on top right here. Fx minus fgx minus fk is equal to m times 0 meters per second squared. So this is going to cancel out. And I'm going to plug in all my all the forces I defined into this one right here. So fx I defined to be f cosine of theta. Fgx is mg sine of theta. Fk is mu times mg times cosine of theta plus f sine of theta, and this side is going to be 0 because this term is 0 now. Okay, so the first move I'm going to make is add mg sine of theta and mu and all of this over here to this side, leaving only this term on the left side. So f cosine is going to be equal to mg sine of theta plus mu times mg cosine plus f sine of theta. Okay, so now I'm going to divide cosine over, leaving me with just f on this side. So f is going to be equal to mg sine of theta plus mu times mg cosine theta plus f sine of theta, and divide by cosine. Okay, so right now I'm going to distribute my cosine at the bottom to each term on the top. So this and this is going to combine to make tan. So I have mg tan right here. And this up here is going to be wait, first of all, I'm going to distribute mu to each of these terms in here first. So that leaves me with mu mg cosine of theta, and then divide by cosine of theta, so this cancels out. So I have plus mu mg, and then this right here, so I have mu times f sine theta. Sine of theta divided by cosine of theta is tan theta. So I have mu times f times tan of theta. So that was a two-step move. Alright, so now what I do is I'm going to subtract this term right here to this side because I want to combine the f's. So f minus mu f tan theta is equal to mg tan theta plus mu mg. Okay, so now I'm going to factor on f. So that gives me f times 1 minus mu tan theta is equal to mg. This time I'm going to also factor out something, and that is mg. So I have tan theta plus mu. Okay, so now I'm going to divide this right here to this side to isolate for f. So my equation for f finally is going to be equal to mg times tan of theta plus mu divided by 1 minus mu tan theta. So that's my equation for f. Now, the second part of part C, as a reminder, we are asked what relation must theta and mu satisfy in order for this solution to be physically meaningful. Okay, so our f must be, our f must be greater than 0 since the block is traveling up the incline. So for this expression to yield a positive answer for f, the numerator has to be equal to something positive, and the bottom has to also equal to something positive. Okay, so for the top, I'm going to ignore f, m, and g because they are the constants that are already positive. So I'm going to focus on this one right here, this term in parentheses. So I want this to be greater than 0. So numerator tan theta plus mu must be equal to 0, greater than 0. So the relationship that the numerator must satisfy is, so I'm going to subtract mu over to the side, so tan theta is greater than negative mu. So this is one of the conditions that mu and theta must satisfy. Okay, for the denominator, I also want it to be greater than 0. So denominator, so 1 minus mu tan theta must be greater than 0. I'm going to add mu tan theta to this side, so 1 is greater than mu tan theta. I'm going to divide mu over, so 1 over mu is going to be greater than tan theta. So this is another relationship that mu and theta must have. Okay, so these are conditions right here. And I'm going to verbally explain it. So for this expression to yield a positive f, tan theta must be greater than negative mu, because this relation ensures that the term tan theta plus mu yields a positive, use a positive number to make the numerator positive. Same goes for the denominator. So another requirement is this. Tan theta must be less than, I'm just flipping the equation around because I want theta to go first. So tan theta must be less than 1 over mu, because this ensures that the term 1 minus mu tan theta yields a positive answer. No, not answer, number. To make the denominator positive as well. Alright, so these are 2 requirements and we're done.